In the previous video, we saw that the maximum efficiency of a silicon solar cell, just by looking at the solar spectrum here, is about 28%, but commercial silicon solar cells get around 10 to 15% efficiency. So only 10 to 15% of the energy of the photons is converted to electrical energy. How can we make our solar cells more efficient? And how can we capture more of the solar spectrum? Because we see, for example, for gallium arsenide solar cells, they're capturing this portion of the solar spectrum. Silicon is capturing this portion of the solar spectrum. But we're not capturing the entire solar spectrum with either of those two semiconductors. One way that we can capture more of the solar spectrum is using these structures. And these are heterojunctions because the band gap energy of this type of p-n junction can be different. Up to now, we've assumed that the band gap stays constant throughout the p-n junction, but in heterojunctions, we no longer have this assumption. So, for example, in the band diagram on the left, that's labeled figure 0.412, the band gap of the n-type side of the p-n junction is greater than the band gap of the p-type side of the junction. In thermal equilibrium, we still have the Fermi levels of the n and p side lining up. We still have band bending of the conduction band and the valence band. The difference here is that because the band gap of the n side is greater than that of the p side, there can be some discontinuity in the conduction band and in the valence band, labeled as this delta EC and this delta EV. But for a solar cell, what this means is that if you have photons with a shorter wavelength or a higher energy, that wasn't a very good drawing. Okay, so shorter wavelength or higher energy, they can be absorbed in the wider band gap material, and photons with a lower energy can be absorbed in the smaller band gap material. And therefore we can cover more of the solar spectrum using this kind of structure. The diagram on the left shows a different type of heterojunction structure. Here there is a heterojunction only on the p-type side of this junction. So there is one type of material, p-type dope material here, another p-type dope material here, and then an n-type material here. So here, this difference in p-type materials creates a difference in the band gap. Higher energy photons can be absorbed here. Lower energy photons will pass through this material and get absorbed at the p-n junction.